Hey guys, welcome to Real World Problems with Log. And this is going to be level 1 because we're not going to have to come up with any equations. They're already going to be given to us. So we're going to go through and solve two problems that involve real world situations. You'll see some sites, some works cited on on them as well. So you can see that this information is true and real and coming from actual sources. So let's begin. So our first problem here is a computer science problem. And a popular problem in computer science is we need things to compute faster, because the faster that they can compute, the less CPU kind of space they'll take up, and the more things your computer can do at once. So computing time is a really big deal. So this says computer programs perform many kinds of sorting. It is preferable to use the least amount of computer time to do the sorting, where the measure of computing time is the number of operations that the computer needs to perform. We discussed two methods of sorting, so we're going to look at this thing called bubble sort and this thing called heap sort. It is known that the bubble sort algorithm requires approximately n squared operations to sort a list of n items, while the heap sort algorithm, so now we know heap sort, requires n times log base 10 to the n, which we're just going to call log n, to sort. Okay. To sort 100 objects, how many operations are required by the bubble sort and the heap sort? Okay. For A, so for bubble, we know, for bubble sort, we know it's n squared, and we're going to sort 100 items. So for bubble sort, it's going to be 100 squared. Let me just make sure I have the correct amount of zeros here. 100 squared is 10,000. Okay, and heap sort is n log n. So n is 100 times log of 100. Okay, so 100, what is log of 100? Well, it's log base 10, so 10 to what power is 100? Oh, 10 squared is 100, so log of 100 is 2. So for heap sort, it would only take 200 operations. For bubble sort, it would take 10,000 operations. Okay, obviously heap sort takes way less. Okay, B. Make a table of the number of operations required for bubble sort to sort a list of n items, with n ranging from 5 to 20. So n, we'll call this OPP, or operations, 5 to 20 in steps of 5. So 5, 10, 15, 20. This will be for bubble. And then rework part B for heap. So we'll just make both of these. So for bubble and for heap. So n operations. And again, we're going to look at this for 5, 10, 15, and 20. So the algorithm for bubble sort is n squared. So 5 squared is 25. 10 squared is 100. 15 squared is 225, and 20 squared is 400. Okay. For heap sort, so heap, remember, is n times log n, log base 10. Okay, so what is 5 times log of 5? Let's see, 5 times log of 5. I'm going to round this, so this rounds down to 3. What is 10 times log of 10? Well, log of 10, 10 to what power is 10? Well, 1. 10 times 1, this will be 10. For 15, this will be 15 times log of 15. So 15 times log of 15. Rounded, this will round up to 18. And 20 log of 20. See, 20 times log of 20. This gives us rounded to 26. So here's B and C. So you can see for bubble sort, bubble is way bigger as far as operation goes than heap sort. So D says, which algorithm, the bubble or the heap, is more efficient and why? Well, heap sort is going to be more efficient because it takes less operations to run the same amount of items, okay, which means less computing time, less CPU space. So heap sort is the winner here. Next, in the same window, graph the functions that give the number of operations for bubble and for heap. Let n range from 1 to 20. Which function is growing faster and why? Note that you still have to choose the vertical scale carefully, blah, 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 blah. All that to say that I graphed this already, and here it is. Okay, can you guess which one is which? The red line is bubble. The blue line is heap. So bubble takes off. So here's one is like about right here. So from 1 to 20, heap stays relatively low. Look, heap doesn't even get up to 100 at all, where bubble takes off to up to 400 by the time we get to 20. Okay, so here's the graph of bubble versus the graph of heap. So as far as computing times and sorting algorithms, heap is the way to go. So that was that problem. This next problem is going to have to deal with pH. Okay, so pH is the scale that measures acidity. I know a lot of you guys are simultaneously doing chemistry courses, so this may make a lot of sense to you guys. So for ecology, the pH scale measures the level of acidity of a solution on a logarithmic scale. A pH of 7 is considered neutral, so most like pure distilled water has pHs of 7. If a pH is less than 7, then the solution is acidic. So the lower the pH, the more acidic, and the higher the pH, the more basic. So anything above 7 is basic, anything below 7 is acidic. Since the pH scale, though, is logarithmic, a single unit decrease in pH represents a 10-fold increase. So a single unit decrease is a 10-fold increase in the acidity level. So for instance, if we go from a pH from 4 to 3, it's not, oh, that's more acidic by a factor of 1. No, it's 10 times more acidic. So it's not a linear scale. A. The average pH of rainfall in the northeastern part of the United States is 4.5. So the pH in the northeast is 4.5. Normal rainfall has a pH of 5.5. So normal is 5.5. Northeastern is 4.5. How many more times acidic is the rainfall in the northeastern on average? So explain. Well, it's a drop of 1 on the pH scale, but a decrease of 1, as it says right here, a single unit decreased represents a 10-fold increase in acidity. So it's a decrease of 1. So the northeastern rain is 10 times more acidic than normal rainfall. Okay, so 10 times more acidity because it's a drop of 1 on the pH scale. Okay, so that was A. B. Because of increases in the acidity of the rain, many lakes in the northeastern U.S. have become more acidic. The degree to which acidity can be tolerated by fish in these lakes depends on the species. The yellow perch can easily tolerate a pH of 4, okay, which we know is pretty acidic, while the common shiner cannot easily tolerate pH levels below 6. So it looks like the yellow perch and the common shiner, both these fish can't probably exist in the same acidic waters because one of them is going to have a problem. So which species is more likely to survive in more acidic environment and why? Well, that would be the yellow perch because it can tolerate up to 4.0 pH, which is more acidic. So the yellow perch can tolerate up to 4 in pH, which is more acidic, so this guy can tolerate a more acidic environment. What is the ratio of the acidity levels that are easily tolerated by the yellow perch and the common shiner? So yellow perch can tolerate easily a 4.0 pH. the common shiner can tolerate a 6.0 pH. So the yellow perch can tolerate. So every time we drop pH, it's a 10-fold. So from 6 to 5 is 10. From 5 to 4 is 10 times more. So it can tolerate 10 times 10 more acidity. So 100 times more. So because it dropped 2 pH levels, that doesn't mean it dropped by 20. That means it dropped by 100, tenfold. So 10 times every drop in pH. So from 6 to 5, that was 10. And then from 5 to 4, multiplied by 10 again, that's 100. So the yellow perch can tolerate 100 times more acid than the common shiner can. And that's exactly why. So I hope that helped. There were 2 examples, computing time as well as some ecology with some acid rain. Both 2 very real examples, and I hope that helped explain A, how logarithms are used kind of in the real world, and B, that we could actually work out some logarithms and some word problems. So I hope that was helpful, and I'll see you guys in the next video.